Types of energy. You may have heard me occasionally talk about work in joules and then also slip in the term energy, which is measured in joules. And so I see a few of you working on the homework. I'm going to say if you can zone in, that'd be better here if you can. Thank you, thank you. First of all, in general, when we're talking about work, a force that is in the same direction as the motion, like F1 in this picture, does positive work. A force that is opposite to motion, like F2, that does negative work. Usually friction does negative work, for example. Although work can be positive or negative, it's not a vector. It has no direction. So what does negative work really mean? Let's hold that thought. Instead, we're going to define energy. What's energy? Energy is the ability to do work. If an object has energy, it can apply a force over a distance. Okay? So, for example, if I take this bowling ball and I drop it on Alex's head, when it hit him, would it apply a force over a distance? Does it have the ability to do work? So does it have energy? Yes. Okay. Energy is a tricky concept because you can't exactly see it. You have to realize that it exists. There are many forms of energy. One of the most important one is the energy of motion, which we call kinetic energy. My abbrev for kinetic energy, Ren, is KE. And so if you look, Diego, on the formula sheet, if you see a KE in the work section, that's kinetic energy. Another form of energy is heat, usually created by friction. Another form of energy is gravitational potential energy. Now, potential means stored. So gravitational potential energy is stored energy due to an object's height. I'm going to write that down. Stored energy due to an object's height. Okay. There's also chemical potential energy. So you can store energy as chemistry, gunpowder, or the food that you eat, for example, is a great example of stored chemical energy. Sound is a form of energy. There's elastic energy. When you stretch a rubber band, you're applying a force over a distance, and you can use that to do work. You can apply a force over a distance. Nuclear energy is a form of energy. There are many different types of energy. So the key idea, Elias, is if an object has energy, it has the ability to do work. It has the ability to apply a force over a distance. In this course, we're going to look at mechanical energy. That's a terrible. Mechanical energy, which is broken down into two types. Kinetic, that's the energy of motion. If an object is moving, when it hits you, it has the ability to apply a force over a distance. It has the ability to do work. And potential energy, stored energy. My abbrev for kinetic is KE. My abbrev for potential is PE. And that's when you saw that PE on your formula sheet as well. That was potential energy. By the way, this is what explains negative work. When you do negative work on an object, what that really means is the object is losing energy. Positive work, the object is gaining energy. Okay? Put the phone away, you're not that important. Here's a nice summary of what we've talked about so far. Put your pencils down, look up. Come on, video player.
In physics, the concepts of work and power help us understand and explain lots of things in our universe. Let's start with work. Positive work is the energy we put into a system, and negative work is energy that's transferred out. Think of positive work as money being added to your bank account, and negative work as money taken out. In the metric system, work and energy are measured in joules. As an example, let's take a beautiful old mechanical grandfather clock. We transfer energy into the clock when we turn the crank to raise the heavy metal cylinders inside the clock.
So an old grandfather clock, when you wind it up, you're raising weights up, you're giving them more gravitational potential energy because you're applying a force over a distance, mgh, and you're storing that in the weights. As they slowly drop down, they're giving that energy to run the clock.
When we do this, we're doing positive work, adding energy to the clock. And that energy is stored as gravitational potential energy. We can calculate the amount of work done by multiplying the force we apply times the distance over which we apply the force. To raise the metal cylinders, we need to apply a force equal to their weight. That is, equal to the force of gravity pulling downward on the cylinders. These cylinders weigh 300 newtons, which is pretty heavy, about as much as a small child. And if we lift them 1/2 meter, then we do 300 newtons times 1/2 meter, or 150 joules of work. Power is the rate at which energy is transferred. When we say rate, we mean the amount of energy transferred per unit of time. In the metric system, power is measured in joules per second, or watts. The term watt goes back to James Watt, who came up with the concept of horsepower to measure the amount of power produced by a typical workhorse. James Watt was a producer of industrial steam engines, and he wanted his potential customers to be able to make comparisons between his steam engines and a familiar quantity, the power they could get from a working horse.
So I did my rant yesterday where I said the horsepower has nothing to do with horses. It was really a made-up number, but it was a great selling tool. We still use it, even though horses are not part of our economy.
This was such a useful idea that the metric system unit for power, the watt, is named after James Watt. Following in James Watt's footsteps, let's compare the amount of power it takes to run this grandfather clock to the power we'd need to run a bright 100-watt light bulb. We can measure the power a person uses to wind the clock by dividing the amount of work they did by the time it took them to do it. If it takes 1 minute or 60 seconds to lift the weights, then they are doing 150 joules divided by 60 seconds, or 2.5 joules per second of work. They're adding energy to the clock at a rate of 2.5 watts.
Small wattage. Remember, I also said, Elias, that power is tiredness. You don't get tired winding up a grandfather clock. You're not going to be huffing and puffing at the end of it. You're applying energy, but very slowly. Okay?
You'd need about 40 times as much to run a bright 100-watt light bulb.
Have any of you at Science World or another sciencey, worldy kind of place pedaled a bike to make a light bulb light up? Have you done that? You got to go pretty hard. Okay, 100 watts is a fair bit of power.
Before we let the clock run, the energy is stored as gravitational potential energy of the cylinders. It's like your bank account when you have just deposited money. But if we let the clock run, the cylinders slowly move downward. Energy is leaving the clock. In fact, when the cylinders get to the bottom, all the energy that we put in will have left. So how much power does the clock use? That is, how many joules of energy per second leave the clock if it takes 5 days for the cylinders to return to their original position? We can figure this out because we already know how much work we did when we lifted the cylinders, 150 joules. But this time it took 5 days rather than a minute. 5 days is 5 times 24 times 60 times 60 again, or 432,000 seconds. So we divide the work done by the time and find an answer of about 0.00035 joules per second, or about 0.35 milliwatts. That's a tiny amount of power. This clock uses so little power that you could run almost 300,000 clocks using the same power it takes to run one 100-watt bulb. That's right, you could run a clock in every house in a medium-sized city with that much power. That's a pretty amazing conclusion, and it took knowledge of work and power to figure it out.
So grandfather clock's a great example of work and power and energy. Back to our notes, potential energy is stored energy. There are many types of stored energy, chemical energy in gunpowder or in food. But a really good example of stored energy is a bow from a bow and arrow. Suppose you pull a bow back and it takes 250 newtons of force to pull the arrow back 0.78 meters. How many joules of energy are stored in the bow? Well, the work that you did was the force times the distance. And you're going to notice I'm kind of using work and energy interchangeably, and the reason is, what is energy? It's the ability to do work. They're both measured in joules. So the amount of work that I did added energy to this system. Alex, what was the force that we used in this? How far back did we pull it? How many joules of energy are we storing in the bow as potential stored energy? 250 times 0.78, 195 joules of energy. So here's the question. When we release the string, what happens to that energy? It gets transformed. And it gets transformed into a different type of energy, kinetic, the energy of motion. Where does it pass the energy to? The energy leaves the bow and gets transferred to what object? Starts with letter A. The arrow. The arrow, if it was a purely 100% efficient transfer, the arrow would now possess 195 joules of energy. So, transferred to arrow as KE, kinetic energy. And in fact, based on that, if you know the mass of the arrow, you can calculate how fast the arrow should leave the bow. Put your pencils down, look up. The physics behind a bow and arrow or a slingshot are wonderful. Have we applied a force over a distance? Have we done work? Yes. Have we stored energy in this system? Yes, there is a great deal of potential energy stored in this system. Where will that energy get transferred to? The girl. In what form? Fair bit of kinetic. Okay? beautiful physics there. That, I think that was a video from Utah that they just set that up. I'd be concerned about my neck in that, but there is a resort, I think it's in Minnesota, that does offer this, but you're gonna wear a neck brace and padding and a helmet and gloves, but they do offer something like that. With good padding, certainly be willing to try it. That one there looked a little unsafe to me. I think there'd be a fair bit of whiplash on the release. But if you gave me a good neck brace and some good padding, I think I'd be willing to try that. You may have seen when I was in Florida, there was an amusement park there that had something like this where two people got into a round cage. They were strapped into a seat. The round cage was being held up by slingshot string. It got pulled down to the ground instead of sideways, and then it got released and shot up and bounced back and forth on bungees. That I'd be willing to try as well, because good physics. Okay? So beautiful physics there. When you turn the page, is it turn the page? I think it's turn the page. So when you stretch a rubber band, you're storing potential energy in the same way as when you stretch a bow or when you stretch a bungee cord. A battery has stored electric potential energy, but in this unit, we're going to focus mostly on one specific type of potential energy, gravitational potential energy. This is the work that you have to do against gravity in order to change an object's height. And we're going to figure out the equation by using Alec as a guinea pig. Alec, I won't let you get hurt. Okay? No. Here's an object, yes. Do you think right now it has more stored energy or less stored energy than right here? So I think in our equation, I think a height should appear. Yes, and it should be on the top. Because as height gets bigger, energy gets bigger. Okay. Leave it. Which object do you think has more potential energy? So you know what? I think an M for mass should appear in our equation. And then the other thing is a bit subtle, but I think on the moon I would be doing less work to raise this up. So I think G should appear in the equation. Diego, what was the PE equation that you read from the formula sheet?
P equals mgh.
So Diego said PE equals mgh. I should be very specific. PE from gravity equals mgh. Or if you know the object's weight in newtons, PE equals the force of gravity times h. That's the amount of stored energy that an object gets by lifting it. We use that one all the time. As an example, all of our electricity in BC is based on this. What a dam does is it causes the water behind the dam to slowly increase in, I'm looking for a word that starts with the letter H, height, thereby giving that water more stored energy. At the bottom of the dam is where we put the turbine, so we have the water push out through the turbine, we turn it into rotational energy, we turn that to electrical energy, but it all starts with a dam is an easy way to get nature to build up mgh. Not free energy, energy isn't coming from nothing, it's coming from the sun and more complicated process, but it's not free, but it's pretty good. Jaden has a mass of 75 kilograms. What's his weight? Isn't his weight 75 kilograms? Oh no, that's his mass. What's his weight? Well, weight is Fg, so it's going to be really close to 750. 735? Units? Okay. When Jaden jumps, He can raise his center of mass 75 centimeters. Stop. Cross out 75 centimeters. 75 centimeters. How many meters is that? Good. 0.75 meters. Yeah, if you had that kind of a jump. So at the top of his jump, how much potential energy does he possess? Well, his gravitational potential energy, it's mgh, or it's the force of gravity times h, because that's what mg is. It's the obvious one, times h. Since I figured out the force of gravity is 735, I'll use that, times 0.75. How much energy does he possess at the top of his jump? Sorry? 0.25? Where did that energy come from? The chemical energy stored in his body and the food that he ate. Okay? Can you jump up and down forever? No. Why? Because each time you jump, you're using up some of your body's chemical energy, and your body doesn't have an unlimited source of chemical energy. But it's also why skipping rope is a good way to get exercise or to lose weight, because you are burning a fair bit of energy in that particular process. How much gravitational potential energy does an object have if it's on the ground? Well, potential energy is mgh. So what would that be as a number exactly? Yes. Okay. Which maybe is Captain Obvious, but sometimes it's worth pointing out the obvious just to help us understand what our boundaries are. So potential energy is any stored energy, but specifically gravitational potential energy, mgh. The second one is even more interesting, kinetic energy, the energy of motion. What's the equation? Well, we're going to figure out what the equation depends on. I'm not going to walk over to poor Alec this time, but if I threw that small mass at Alec and it hit him in the face, could it do work? Could it apply a force over a distance? Does it possess energy? Okay. If I threw it harder, would that, do you think, do more work or less work? So the equation for kinetic energy should have a V in it. Yes? If instead of the small mass, I threw the bowling ball, would that do more work or less work? So the equation should have an M in it, but it's a bit less intuitive. Here is the equation for kinetic energy. It's a half mv squared. And I'm not going to derive it with you. If you want to see me during a flex block, and I'll derive it with you. But kinetic energy is a half mv squared. And although you don't realize it, that squared dominates your life in ways you can't imagine. It totally dominates your life. Okay. I looked up the specs online for a .357 Magnum bullet. It weighs 8.1 grams. Stop. 8.1 grams. How many kilograms is 8.1 grams? Well, how many grams in 1 kilogram? First of all, how many grams in 1 kilogram? What's kilo mean? Worth memorize. Okay, 1,000. So divide by 1,000, it's 0.0081 kilograms. And travels at 490 meters per second. For nerd trivia, the speed of sound is 343 meters per second, so this bullet is going faster than sound. There would be a sonic boom associated with it. How much kinetic energy does it possess? Well, kinetic energy is a half mv squared. And I gave you that formula on your formula sheet, probably right next to the potential energy equation, I hope. That would make sense to me. So it's going to be 0.5 times 0.0081 times 490 squared. A bullet gets its energy not from its mass. A bullet gets its energy from its v, from its speed. 0.5 times 0.0081 times 490, don't forget the squared. And I get 972 joules of energy. Yes? Suppose a car has a mass of 1,000 kilograms, nice round number. How much kinetic energy is required to reach a speed of 5 meters per second? Well, what's our new equation for kinetic energy, Kieran? A half mv. You know what? I bet you with these numbers, Kieran, you can even do it in your head, because you're right, 0.5. What's m? And then 5 squared. What's 5 squared? 25. This is 500 times 25. Maybe you can't do that in your head. Double check me. I think it's 12,500. Yeah. And this is energy. What are the units for energy? Joules. Okay. Sorry, I got to shrink it back down again to fit it on one page. So, how fast were we going in A? And if you're working on other stuff, this is where you might want to zone in, because this is probably going to be an important concept. Oh, we are. We can pause right now. So we had our room cleaned interruption, but we're back. I said to you that squared dominates your life. So here's what I want you to notice. To go 5 meters per second takes 12,500 joules of energy. To go 10 meters per second, is that going to take twice as much because it's twice as fast? Let's find out. Kinetic energy is a half mv squared. It's going to be 0.5 times 1,000 times 10 squared. Kieran, I'll bet you this one you can do in your head. Because what's 10 squared? What's 10 times 10? 100. What's half of 1,000? It's 500 times 100. It's 50,000. Is that twice as much as 12,500? No. How many times bigger is that? Could you on your calculator, could you go 50,000 divided by 12,500? How many times bigger is that? What? 4 times bigger. Twice as fast takes 4 times the energy.
Oh, it's a square.
What? Alec, you get a candy. Talk to me. What?
Square.
That squared dominates everything. So to go 3 times as fast, like in C, what's 3 squared? 3 squared. It's going to take 9 times more energy. So if I want to go, and you can write out the numbers if you want to, it's going to be 0.5 times 1,000 times 15 squared. And there's 2 ways you can get that. You can crunch. If you all go 0.5 times 1,000 times 15 squared, I'm going to go 12,500 times 9, 3 times faster, 9 times the energy, 3 squared. And I'm willing to bet that that's the answer that you got when you went 0.5 times 1,000 times 15 squared. First of all, what this means is as you're driving and you start paying for your own gasoline, the faster you go, the more fuel you're burning at a much faster rate. If you're going twice the speed limit, you're burning 4 times the gas, not twice the gas. So I have a sailboat, and I can get somewhere when there's no wind with my motor going at what we call cruising speed, which is at about 6 knots, and my engine just sips the fuel. If I go twice as fast, 12 knots, I'm going through tanks of gas like I wouldn't believe. I have to completely change my outlook. I can't go as big a distance because I'll be burning fuel up so much faster. So I've learned I just go slower and get there because I'm paying for the gas out of my own pocket. So, example 6. Suppose an object has a kinetic energy of 5,000 joules. How much kinetic energy is required to double its speed? Not twice as much. What was the revelation that you had? It started with letter S and had a Q in it. So what's 2 squared? It's going to take 20,000 joules of energy to double its speed, not 10,000. What if we want to triple its speed? Elias, what's 3 squared? 3 times 3. Yeah. It's going to take 9 times 5,000. It's going to take 45,000 joules to triple its speed. Not 15,000. And most people would think, oh, just 15,000 joules, Mr. Do. No. Way more. What if we want to quadruple this object's speed? How much more energy will it take? How many times more energy will it take? What's 4 squared? 16 times more energy. So that squared, a half mv squared, that explains a bunch. For example, it explains why over the past 30 years in sports equipment like golf clubs or tennis rackets or hockey sticks, they've become lighter, not heavier. I know there's an M in the equation, but if you make the M smaller, you can swing it faster, and when you swing it faster, you get squared more energy when you hit the ball. So it's a trade-off. I realize you're losing a little bit with the mass, but you more than make up for it with that squared. So for example, as a golfer, they always talk about club head speed. How do you increase club head speed? You make the club lighter. You lose a bit of the M, yes, but you swing faster and you get way more energy out. I mean, you may have, if you've ever seen a set of golf clubs from 30 years ago, they're brutes. Nowadays, no, they're lightweight. And it's counterintuitive because a lot of people would think, wouldn't you want a heavier club head to get it to go further? It's not about the mass, it's about the kinetic energy. And the V has the squared on it. Hockey sticks, same. Tennis rackets, same. The tennis rackets that I grew up with were these monstrous brutes. Now they're lightweight. Okay? This is also why it's more difficult to speed up once you already have kinetic energy. So how many of you have noticed if you're riding your bike, I'm going to assume all of you have ridden a bike, to go from 0 to 5 meters per second, it doesn't take much effort. But to go from 5 to 10, which is still a 5 meter per second increase, takes way more effort. And once you're going fast, to go even faster, say from 10 to 15, takes way more effort. Even though it's the same 5 meters per second increase, that squared is kicking in. That squared is kicking in. And now I got to be serious with all of you as young, stupid wannabe drivers. This is also why damage to occupants in car accidents is so dramatically different between an accident at 20 kilometers per hour and an accident at 80 kilometers per hour. The 80 kilometer per hour car accident will not experience 4 times more damage. How many times more damage? 16 times more damage. Also, it will take 16 times more distance to stop. And I've just explained with that a big chunk of the car accidents out there. If you're going twice as fast, Ren, it's going to take you 4 times further to stop than you're used to. Not twice as fast, twice as far. If you're going 3 times as fast as you're used to, it's going to take you 9 times further to stop. And nobody thinks that. So of course they're going to run into something, or going around a corner, they're going to go past the corner and overshoot. That squared dominates your life. but it also makes for good roller coasters. A 25 kilogram mass object has a kinetic energy of 924.5. How fast is it traveling? Braden, what's this question wanted me to find? How what? You know what? It wants me to find the V. So let's write down our kinetic energy equation. Ke equals a half mv squared. Okay, humans. How would I get the V by itself? Well, how would I move the m over? How would I move the m over? I heard someone whisper it. You're right. Divide. This 1, it's multiplying the V. So I would divide by 1, but will dividing by 1 make a difference at all? Okay. This 2, since it's on the bottom, is dividing the V. So dividing by 2 on the right is the same as what on the left? Yep. So I would have this 2 times the kinetic energy divided by m, and also divided by 1, but I'm not going to write that. That equals v squared. Everybody, how do I get rid of a squared? So here is yet another way to find a speed, and I don't know how many I've given you since Physics 11 and Physics 12, but this is what I'll use if I notice, oh, they've given me energy and a mass. So let's crunch the numbers. V is going to be the square root of 2 times 924.5 divided by 25. How fast is this object traveling? And this is a really useful one. This is what, you don't know how yet, but in a couple of days, this is what you can use to figure out how fast you're going at the bottom of the first roller coaster hill. And I think if you calculate that while you're standing in line, it makes the ride better if you know how fast you're going when you get there. It just adds to the experience. How does it not? 2 times 924.5 divided by 25. Oops, I'm missing a 924. Oh, that was wrong. 924.5 divided by 25, and then square root answer button. 8.6 meters per second. So point Braden, I'm saying is, look, if I give you basically this equation has 3 variables, Ke, M, and V. If I give you any 2, Braden, I figure you can find the third. So let's look at a roller coaster. Suppose you know that a 350 kilogram roller coaster has a kinetic energy of 137,200 joules at the bottom of the first hill. And I'll show you later how you can calculate how much energy it will have. Well, how fast is it traveling? Ke equals a half mv squared. Get the v by itself. Let's see. The Ke stays where it is. Divide by m times by 2. That gives me v squared. How do I get rid of a squared? So this roller coaster at the bottom of the first hill, 2 times 137,200 divided by 350, square root of that. How fast will we be going at the bottom of the first hill? How fast? 28 meters per second? Could you times that by 3.6? How many kilometers per hour?
100.
That's a good coast. I'm going on that. That's a good coaster. Let's suppose you're designing this roller coaster and you want the speed at the bottom of the first hill to be 28 meters per second. How high do you have to build the first hill? B, if all of that kinetic energy came from potential energy, how high is the first hill? Diego, what was our equation for gravitational potential energy? the one that you accidentally read out earlier.
T equals MGH.
So if PE equals mgh, but I know that the PE is 137,200 because they told me that's where all the kinetic energy came from. How would I get the H by itself? What's the M doing to the H? So, what's the G doing to the H? So are you telling me I divide by mg? You would be correct. H is going to be 137,200 divided by mg. And now we're getting the very basics of roller coaster design. It's going to be 137,200 divided by what was M, 350. What was G, 9.8. How high does the first hill have to be? Even? What if, due to building codes, I'm only allowed to build a hill 36 meters high? But I still want you to go for 28 meters per second at the bottom. What do I do? No. Dig a hole. I go 4 meters down into the ground. And you'll see coasters that have done that. Okay? Or especially if where they're building the coaster, there is a natural ravine that was carved by nature, the engineer is going, oh, heck yeah, that's extra meters per second. I'll take that. For free? Sure. Okay? So the relationship between roller coasters, height and speed, the potential energy from the top of the roller coaster turns into kinetic energy at the bottom. And if you've ridden coasters, you've clued in. Bigger hill, faster coaster. But here's the physics of why. How high would we need to lift a 65 kilogram object to give it a potential energy of 15,208 joules? Diego, I think this is the same thing we just did, because this is asking me how high. I think B was also asking how high. So I think PE is mgh. How did we get the H by itself, Diego? More specific? Divide by what? Yeah. Yet another way to find height, and I've given you several over this course, is, I guess, the potential energy divided by mg. It's going to be 15,288 divided by 65 times 9.8. Sarah, here's my point. In this equation, there's PE, M, G, and H. If I give you any three, I think you can find the fourth and get it by itself. Don't know if I'd ask you to find G. Well, I guess I could make a roller coaster on a mystery planet and you could find G on the mystery planet, which would be kind of cool. So maybe I'll do that. But typically, I'll ask you to find the mass, the potential energy, or the height. Is there more than one thing on the bottom? Yes. Better put brackets around the bottom. Oh, 24? I must have spent a lot of time making these work out nice. Fair warning, they probably won't in the homework because I don't care enough. 24 units for height meters. So let's look at some applications. You may have seen, if they're building a new building, a pile driver pounding a beam or a post into the ground. Suppose I want a 2,500 kilogram pile driver to hit the ground at 18 meters per second. First question, how much kinetic energy does it need? How do I find kinetic energy? KE equals? It's on your sheet. So it's going to be 0.5 times 2,500 times 18. Don't forget the squared. By far the most common mistake. Kids write the squared, they think the squared, they forget to type the squared on their calculator because their brain has already checked off. I wrote squared. You get 405,000 joules? Okay, so if all of that kinetic energy comes from potential energy, how high do we lift the pile driver in order to have it hit the ground at 18 meters per second? Oh, Diego, what's B asking me to find? How what?
How high?
Oh, what was getting the H by itself in the potential energy equation? H equals, what was it? PE over, oh, easy peasy. How much potential energy do we need? Well, that much to turn it into kinetic. M was 2,500. G was 9.8. Yeah, here's the messier answer where I stopped caring about you all. So 16.5 meters, I think I get. Double check me. Okay. Last one, and then one of my favorite all-time videos. A person is running at 7 meters per second. If they have a kinetic energy of 1,764 joules, what's their mass? Oh, I guess kinetic energy, let's get the M by itself. Kinetic energy was a half mv squared. How would I get the M by itself? Sorry? You could either divide by 0.5 v squared, and I would give you full credit, or I like to divide by 1, ignore it, and times by 2, because timesing by 2 and dividing by half is the same thing. So yeah, M is 2ke over v squared, or ke over a half v squared. Same equation. Okay, let's crunch that. 2 times 1764 divided by 7 squared. This person, or object person, has a mass of 72 kilos. So typically in a roller coaster, that first hill is giving you potential energy, and that potential energy is giving you kinetic to get through the rest of the ride. There's a couple of exceptions, like the Incredicoaster, what used to be California Screaming at Disneyland, which shoots you off from the ground, gives you kinetic energy to begin with. But most of them, that big chain that takes you up, they're giving you potential, and you're turning it to kinetic. The Incredicoaster, they're re-theming it after the Pixar movies. What's your homework? Number 1. Number 2. Number 3. 4, 5, 6, 7, 8, 9. So far I'm assigning all of them, but I'm going to give you, 10 is good. I'm going to give you kind of a weird challenge. I'll skip 11. 12 is good. 13. 14. Cross out 15. Cross out 16. 17 is good. Here's your challenge. I gave you a whole bunch. See if you can do it all on your calculator, showing no work and not writing anything. In other words, see if you can go straight to If it's kinetic, a half mv squared, right to your calculator. Or if it's getting the m or the v by itself, right to your calculator without writing anything down. Or if it's potential, mgh, right to your calculator. Or if it's getting the m or the h by itself. See if you can do it. I will take your word for if you only have answers written and show no work. So we've been talking a little bit about energy transformations. A commercial came out in 2004 by Honda, which won a whole bunch of awards that year. See if you can spot a great example of energy transformations, Sarah, are what are called Rube Goldberg machines. Rube Goldberg was a cartoonist who used to illustrate elaborate contraptions, chain reaction machines to perform simple tasks. A good example of a Rube Goldberg machine in front of Science World, outside, you know that contraption that has the balls that roll around on railings and then bounce down and move up? That's kind of an example of a Rube Goldberg machine, but it's not completing a task. Okay?
That thing even works anymore.
It's finicky. Most Rube Goldberg or chain reaction machines are very finicky. In fact, I read the blog about this commercial. So this is a Honda commercial. They wanted to build a chain reaction machine. The goal is they want to close a tailgate on a Honda. That's the goal. So they started out by giving this object some kinetic energy. That's the initial energy source. The rest is all stored in this contraption. These are all parts from a Honda.
Isn't it nice when things just work?
That's one long.
I read the blog on this. It took them 3 months, and by the end, the engineers who were building this were almost going crazy because everything was so finely tuned. They'd have it ready to go, and the semi-truck would go by 3 blocks away, and just the vibration from the ground from the truck was enough to start part of it going reset. So, and they did this with no special effects. So, Mr. Dewitt, can we see it one more time? Let's look at. So we're starting with potential turned into kinetic. More potential turned into kinetic. Again, sliding downhill, turning gravitational into kinetic. This is weird though. Watch these tires. How are they speeding up going uphill? Here's what I think. I think inside the tire, right above the axle, there's a mass. And that mass is falling down, not violating conservation of energy. And as it's falling down, it's causing the tire to rotate. So we're not breaking any rules here. So watch it again, see if you can spot it. I'm certain that's what they've done. They've got a mass above each axle of the tire. And now that you see it, you can kind of see it falling down in your mind and pulling the tire up. New source of energy, electrical energy now from the battery. But then kinetic, and then potential turn back into kinetic. Gravitational potential bounces down back into kinetic. Again, a new energy source, electrical, which activates the windshield wipers. And that's enough for the windows to just blow on that object to knock it over. Just to give you an idea of how fine this was, they have that car balanced on a two-wheel trailer, and lowering the tailgate is just enough to move the center of mass forward, just enough that now it's no longer balanced and it falls
Isn't
forward.
it nice when things just work?
So a really neat example of energy transformations. Thank you for your wonderful patience, my angels. I know that was a long, long time. Stop the video.